calculate the hydraulic grade line, first pass. That means we're going to have our first estimate. Like I said, we used 18s and 24s. So take a look at that table to make sure that you've selected before you have the 18s, you have a 24, 18, and 24. They should look similar to your values here, time of concentrations, and slopes. Now, here's where you first figure out. Right now, the only thing that we don't have filled out, take a look at up here at the top. We have hydraulic gradient, crown, and flow line. So this is the crown of our pipe. This is the flow line. We need to figure out the hydraulic gradient upstream, downstream. Now, I've created a second spreadsheet, so I've taken all the other colors out, so now we're just focusing on the hydraulic grade line. The hydraulic grade line is basically when water starts to fill up into the pipe. It'll start to fill up from the pond, and anything at that elevation is already basically full. So if I projected this out, it automatically fills up to here. Okay, from where we said the design elevation was, it fills up into the structure, and then it starts to fill up to the pipes, flowing completely full. Now, what we're investigating is this hard line that they stage up to into the pipes. Technically, there is a line connecting this, and it is called the HGL, the hydraulic grade line. So that's what we're going to be figuring out. All right, so the very first step is, it says determine the lower end of the hydraulic grade elevation, P8 to out. It says for the outlet pipe, the lower end is the design tailwater. For this example, the design tailwater is the higher of the two. Is at the crown of the pipe, and if we look at our spreadsheet, the crown of the pipe was 6.5, okay? Now, the elevation of the tailwater that we said at the very beginning up here was 8.3. So we know that the tailwater is actually controlling. All right, so that's where the first value comes in, that 8.3 right there. Now, if I look at the cell to figure out the hydraulic grade line, look what it's multiplying by. I need to figure out the full friction, the full friction loss. So what that means is to determine the upper end, we're going to use the lower end elevation plus the full flow friction loss. Full flow friction loss is basically the length of pipe times the friction slope. So here's our friction slope. So I've got this little formula right here. And you all should have it on your sheet also, and you can fill out that cell. So here's the blank sheet down here at the bottom. So this full friction slope here is what the formula you'll be filling out. So on mine, what I have is I've got the length of pipe times the friction slope. 250 feet times that friction slope. And if you look at that friction slope, here's the slope, here's the hydraulic gradient, here's the physical, here's the minimum. You're using, whoops, too far. You're using that 0.18%, okay? Or you could have just referenced this cell here, and that's your friction slope from the calculations. You could have referenced, whoops, don't do that. You could have referenced this cell here, all right? So what we did is, to figure out the upstream HGL, we took the friction slope and added it to 8.3. It's that simple. Next, what we're going to do, and remember what I said, the downstream becomes the next upstream end. So if this hydraulic grade line is here, is at 8.75, I think I said? 74. If this is at 8.74, then the start at the other end is going to be 8.74. All right? So if you take a look at this sheet from, oh, also the 8.74 is going to go for the S6. It's going to be the point for that pipe at the downstream end. So S6 here, notice that the 8.74, that cell references the S8 cell. Now you can also see the patterns that it's making because of, notice it's S6 to S8, S8 to outlet. Whatever S8 is has to share something in common, okay? So the next one says, just to show you the pattern, S7 and S8. So if S8 has a value, then S7 to 8 has to share a value. Okay. And that's the cool thing about writing it this way. Now, wrong one, sorry. So the friction slope we figured out, and we figured out the upper end is to be 8.75. So it should look something like this. Now it says pipe sections 6 to 8 are stubs of that hydraulic gradient, and we don't need to calculate the first pass up through. I went ahead and set it and went back, and if I needed to change it, I changed it. I just went ahead and set it. Now it says determine the lower end hydraulic grade line. The downstream upper end, 8.75, is the lower and crown and end crown elevation of 6.5. Therefore, the lower elevation equals the upper end hydraulic grade line. Now, what they're saying here is, if you look at this pipe, so I'm looking at P7 to P8. Let me switch. I'm going to close this one out. P7 to P8. So I've got the 8.74, and I've got the friction slope flowing full, and it's got my length times my friction slope. What they're saying in this part here, it says, well, which is higher, the hydraulic grade line or the crown of the pipe? So sometimes the crown of the pipe is assumed your highest grade line. Well, the downstream end is only 6.5, so they're saying, okay, we're not going to use the 6.5, we're going to use the upper end. We're going to calculate the upper end. Or I'm sorry, we're going to use the higher from the previous. If the 6.5 was, if the downstream invert here was 9, we would have used 9 here. We would have used the crown there. In this whole section, we don't use the crown of the pipe. All right, so now it says determine the upper end. So we use, like I said, the hydraulic grade line, or the hydraulic friction slope times the length. So we've got the friction slope times the length, and then we just add that to our downstream end. It says the same steps are repeated for the remaining pipes, and this is what the table looks like. So I'll show you really quick. So from 4 to 7, since 4 and 7 shares, we know what 7 is. Its downstream end is 0.85. So the upstream end here is set to, I'm sorry, 0.85 is S5. 0.85 or 0.87 is the downstream end of S4 to S7. Its hydraulic flowing full friction here is going to be the friction slope times the length of pipe, and then you're just going to add it. Now you could literally copy these equations up to the top. The only ones that you have to be really careful with are the ones that are coming in at different locations. You have to be careful of S6 and S5 tying into S7 and S4. All right. So we get the friction slopes all the way up, and we take the friction slopes and multiply it by the length to get our change between our lower end and our upper end. Okay. Now we do the actual analysis of it. It says compare the hydraulic gradient to the standard and adjusted pipes. The standard clearance needs to be 1.3. And this is where I put in the HGL. So what I did is I took the inlet elevation and I subtracted it from the upper end. Okay? That's basically saying I'm taking the HGL of whatever that elevation is and I'm subtracting this upper end. Oops. This is 10.9 and that upper HGL is 9.25. When I subtract these two, it needs to be at least 1.13 or greater. That's what that says, that clearance says. So, I'm checking, I created a little line right here that says, does the design meet the HGL clearance? So this one has 1.65, looks good. This one says it has a clearance of 1.88, S2 to S3. S2 has a 1.88 clearance. S3 has, you take the 11.4 minus the 9.8, the upper HGL, and it's got a 2.3. This one says it's got a clearance of 2.16. This one has a clearance of 2.5 low, 1.74. Oops, that one's only got a clearance of 0.85. So does that meet it? No, this value needs to be 1.13. So what do you have to do? Is if I increased this pipe size to a 24 inch, I would have to go back and redo the calculations from the bottom up to see if that made a difference. Now, I need to figure out the pipe slopes to get that clearance. So on this one, this very first one down here at the bottom, always start at the lower end and increase in size. So this lower end needs to be a 30. It's really close. It's really close. Now, it might be rounding error. You could do a 36, and it meets. The other thing is when you do this, you should also, I'm going to go back to this first pass down, and I want to show you something. And I'm not sure how they arbitrarily picked 18, 18, and 24, because take a look at this. I have full flow, and its capacity, I can carry 4.87 CFS, and I only need to carry 1.92. Why do I have a pipe so large it's carrying so much flow? The next one, I have 3 CFS, and its pipe capacity can still hold 4.42. The next one is 3, and it holds 4.42. Here's the next one. It can carry 5.1, and it's getting closer to where it's almost to capacity. The next one's 4.787, and the next one's 3.12. Is that right? Yep. The reason is because when I forced remember how I told you that this pipe here, S8, has to have 5.48, it automatically forced that slope to have, or that elevation to have, look how big of a drop it is across this pipe. We forced it to be 4.5, 4.5, and it needs to, the upper end needs to be 5.4, and the lower end needs to be, misspoke. The upper end needs to be 4.5. So that makes the lower end of S8 and S7 4.5 to whatever the downstream end is. So we were basically calculating this direction, and then we had to calculate this direction. All right? So that's why there's a drop of 0.9 in that one. So when we're doing this, we're looking at the Qs that the pipe can carry. So why am I doing an 18-inch when I'm only carrying 1.5 CFS? Now here's the one that I thought should have been a warning bell. This one carries only 8.5, but I need it to carry 10.34. So automatically somebody should have said that pipe needs to be bigger, because even flowing full, it doesn't carry the capacity. And this one here is really close. That 5.10 is the flowing full, and it's 4.81. It's close. So are these. So the 18s look good, but some of the other ones can actually go down. So when we change this one to a 30 or a 36, I'm going to go ahead and leave it as a 30. But if we turned this into the county or whatever, or agencies, they would actually require you to force it to be a 36, because this has to be at least the 1.13, and it was 1.17. They can be that big of a stickler about it. They really, really can. The next one, here's the one that's only flowing 1.8. Here's something else. It's got a 1.2 elevation change, or maximum. So you could, and remember what the S6 to S5 is. S6 to S5 can technically be a smaller pipe because it's not part of the main branch. So I could make that as a 15 as long as I still meet the hydraulic gradient. And this is the nice part that changes. All of these calculations change based on that pipe. But here's the bad part, real quick. This is the bad part. When I change the pipe, it changes the Q, which changes the velocity. Guess what? Changes how long it takes to travel in the pipe, which changes the time of concentration, which makes you go back to the IDF curve to get a new Q, or to get a new I. I times CA is going to give you a new Q. So this one's going to be small enough that the intensity duration is only 100th of a change. Your time of concentration is only like tenths of a minute. So your IDF doesn't change your Q value too much. So this one here is a finished one, and I changed them to 15s. Made sure the flow still is carried, but this is a tighter design. So instead of using 18s, I went ahead and used 15s, and down here at the bottom, I used 30s. And I was able to, because of changing the sizes upstream and downstream, I was able to use a 30-inch. All right, I'm going to stop here. For homework, I am going to give you all an assignment that is using this same spreadsheet, so you don't have to redo it. It's going to have the same site plan, same pattern. It'll just have different data that I want you to use. I want you to use a different time storm, and I'll probably give you maybe a little bit different areas going to the pipes. All right, that's it.